Our last speaker today is Yuchen Liu from Northwestern, and he will tell about K-stability and moduli of quartic K3 surfaces.
All right. Thank you very much for the invitation. So it's my pleasure to speak virtually at the Higher School of Economics on this workshop. So I will talk about some recent work on moduli of quartic K3 surfaces using the machinery of K-stability. Okay, so let's get started. So first of all, I want to just give a brief recall of the geometry of quartic K3 surfaces. So here, we talk about K3 surface in the following sense. So you have a surface S. Oh, by the way, everything should work over C. So we work over C. Everything I said, let's see. So we start from a surface. So here S is the projective surface. And we assume it is normal with a singularity condition, which is Duval singularity. And then here L will be an ample line bundle. So this will be a so-called polarized surface pair. But because I want to study a moduli of K3, and sometimes people study, Neff and big line bundles on K3 surface, which is perhaps okay if you want to look at just isomorphism classes. But then the modular functor will not be separated. So that's why I want L to be ample. And then S has Duval singularity. So the K3 condition corresponds to the canonical bundle is trivial. And then the first cohomology of the structure sheet also vanishes. This should be S. So we call such a pair a polarized K3 surface. All right, and then here we'll focus on quartic. So meaning that the degree, so the degree of L is of course defined by the self-intersection of L. And here, throughout the talk, we will focus on the quartic case. Which is the degree of L is equal to 4. So which is quartic. And of course, you can also treat the theory for degree 2, which are generically double cover P2 branch along a sectic curve. And in that case, the theory is much simpler, but there's a kind of motivation probably I will talk about a little bit. And then in general, you want to extend the theory to higher degree K3 surface as well. But so far, as far as I can see, that in order to do K-stability, you always need some Fano threefold containing the K3. So pretty much you can only do up to a certain degree. So this is also one thing I will be interested to extend to more higher degrees. But in this talk, we will just focus on quartic. And then for quartic K3, there's a nice classical classification. So classification of quartic K3s. So there are basically 3 types. So the first type will be called generic, or in other words, this is just quartic surface inside P3. So probably this is one of the most known examples of K3 surface. And this embedding is given by the linear series of L. So the image is a quartic surface. And the second case will be so-called hyperelliptic. So in this case, I don't have an embedding to P3. So actually by Riemann-Roch, you can check that H0 will always be 4. So you still get a map to P3, but in this case, the map is a morphism, which is a double cover over some quadratic surface. So here Q is some quadratic surface. And normal. So meaning that Q can also have singularities, but there are only one possible singular guy, which is the cone over the smooth conic curve. So i.e., I have Q isomorphic to a P1 cross P1 or P112. And then the branch divisor will be a degree 4 intersection with this quartic surface. So if, say, D is my branch curve inside Q, then D will be intersection Q with another quartic surface. So you can think about this type of examples as limit of quartic surface, let's say smooth quartic surface, to a double quadric surface. So then there's a practical way to resolve this map, I think given by Mori, that you can sort of replace this double quadric by a double cover of the quadratic surface. So imagine this is a pencil, then you have a generic smooth quartic surface intersecting Q, and that will be a branch divisor. All right. So this is the second case. And the third case, we call it unigonal. Some people call it elliptic fiber. So in this case, there's a base curve of the linear series. So I call the base curve B. And then if you look at the linear series defined by L minus B, so B is the base curve of L. And then this actually defines a morphism to a rational curve in P3, and this rational curve is nothing but the twisted cubic. And then this fibration is elliptic fiber. And moreover, it's the elliptic surface, K3 surface with the section. Where I think this section is exactly given by this base curve. Okay, any questions?
Well, for the classical part, I think it's very clearly stated.
Okay, thank you. Yeah, let me just make one comment. So we want to study moduli space. So then we should know the dimension of this moduli space. So it turns out this generic guy, it will be 19-dimensional, and all the moduli spaces in this talk will be birational, so they are all like 19-dimensional. And then this hyperelliptic and unigonal, they will all be 18-dimensional. So somehow you can view them as divisors in these moduli spaces. And these type of divisors, they don't occur directly in the moduli of quartic surface embedded in P3, because you can see that they sort of kind of contracted to this quadratic surface may be non-reduced, so twice of it, or the so-called tangent developed surface of C naught. So somehow these two divisors, they getting contracted in the GIT modular space. And the idea we want to sort of recover them is by performing some rational transformation induced from K-stability. Okay, so then let's move on to moduli space. So first of all, there's this nice moduli space, which is I denote by M. So this will be the coarse moduli space of this polarized K3 surface, where so quartic, maybe I should say polarized quartic K3 surface. And what we know about M is indeed not compact, but it is quasi-projective. And as I mentioned, it is dimension 19. And also, because for K3 surface has a nice deformation theory, you know that this is with so-called quotient singularity. So somehow the stack corresponding to this this moduli functor will be smooth, but then there might be finite polarized automorphism. So after you quotient by this automorphism, you see these quotient singularities. And there's another sort of Hodge theoretic explanation. So we have the period map from M to the quotient of a period domain by some monodromy group. So this is so-called period map. And this is an isomorphism because we have the global Torelli theorem. For K3 surfaces. And then here we just take this notation. So F will denote this D mod gamma, although it is isomorphic to the modular space M, but I guess it's more treated as a type of quotient of symmetric space. Yeah. And then inside here we have two divisors, as we just mentioned. So we have HH. This is the period, or if you treat this Kardashev and modular space M to be the same, then this will be hyperelliptic modular space of hyperelliptic K3s. And then we also have the unigonal K3s. So then there will be an open set, which we call M circ. So this is M minus the union of these two divisors. And then you can see that this is like moduli of, okay, perhaps I should keep my notation clear. Yeah, let's just work on M, but later on we will just identify both M and F. So this M circ will be moduli of embedded quartic surface in P3 with dual singularities. So this bigger space M is not compact, but actually you can compactify it using so-called Hodge line bundle. So this compactification you get is so-called Belli-Borel compactification, and it has a relatively small boundary. So we can just record the setup here. So Belli-Borel compactification. So pretty much what we do is we take so lambda is the Hodge line bundle. on this quotient, the arithmetic quotient, and then we just take this F star, which is my Belli-Borel compactification, to be approach of the section ring of the Hodge line bundle. So certainly this gives me, so what we know is Hodge line bundle is ample on this open part. And then this is like a classical result. So we have F C-sims and F star, this is open. And then the complement, which is the boundary of this compactification, is very small. So this consists of curves. So sometimes I say type 2, type 2 locus. Let's say type 2 loci and type 3 loci. So sometimes type 2 loci are called one cusp, and type 3 loci are called zero cusp. So they can be described using some kind of lattice theory, some isotropic subspaces. And then this one cusp, by saying this one, meaning that it's actually one-dimensional, and this will be a modular curve. And the zero cusp usually it's just points. Yeah. Okay. So if you're familiar with the so-called Kulikov model theory, then this type 2 and type 3 loci just precisely corresponds to this one parameter degeneration of smooth or ADEK3s to their corresponding type, Kulikov degeneration. So type 2 degeneration will correspond to a bunch of surfaces whose dual complex are like triangulation of a line segment. So usually you have two rational surfaces at the end of this interval, and then for the intermediate models, you get some kind of elliptic. I think these are surfaces fibered over elliptic curves. And then the double locus will be isomorphic elliptic curves, and that's how you see this modular curve. Basically, just modular of this double locus, which is elliptic curve. And then type 3, you get some kind of S2. So so dual complex is S2. So then if you look at the double locus, of course, you get a kind of like a graph, right? Which if you take further the minimal log canonical center, then you just see points. Okay, any questions?
No, it's still fine at the moment.
Basically, this is for any K3 for this any polarization, right?
Yes, I think it's
not just for quartics. This
yeah,
is general stuff, right?
It's for any yeah, that's right. Any degree, yes. So for quartics, there's a classification of type 2 and type 3. I forgot the actual people who developed this, but there's some paper in the 80s or early 90s that describe everything. Yeah. Okay. Good. So then let's move on to the other aspect of moduli space. So this is so-called classically known as GIT, so geometric invariant theory. So the idea is, of course, I know that that the quartic surfaces, say here, I only care about polynomial being degree 4 without any singularity condition, then this is parameterized. So in P3, this is parameterized by the projectivization of H0 P3O4, right? Which I just denoted by P. Okay, so this is a very large dimensional projective space. And then you have the SL4, which is almost, the automorphism of P3 acting on this projective space. And then this is a classical GIT setup. So therefore, you have the GIT quotient, which I denote by M bar GIT, to be the GIT quotient. So here I take a semi-stable locus and I quotient by SL4. So GIT quotients, it is nice in the stable locus. And what we know from the classical GIT theory is that this M naught sits inside the stable locus. So and then sits inside this GIT quotient. Indeed, there's a new proof using K-stability, but again, we know this there are this containment. All right, and it turns out that for GIT, it's relatively easy to estimate the codimension of the boundary. For instance, you know that if you parameterize like a surface of certain degree, then you look at those surfaces with worse than A1 singularities, then they will have codimension at least 2. So meaning that at the boundary, it will be kind of high codimension. So therefore, you see that the M bar codimension, this is easy to see because I allow ADE singularities in M naught, right? So therefore, if you look at this codimension, then it will be at least 2, and actually it's way bigger than 2. So this tells us that we have a birational map. So we have a birational map from F star to the GIT moduli space. Sorry, this should be birational. It's not certainly not a morphism. Yeah. All right, and this is actually a birational contraction. So phi is a birational contraction. Where it stands, as I mentioned, HH star to the point 2Q, and then send HU star to this point T. So T is just the tangent developed surface of the twisted cubic. We will, talk about it later. But then what's going on is this phi contracted these two divisors to 2 points. But then it's more than that. So if you only blow up these 2 points in the GIT moduli space, you get something that's isomorphic in codimension 1 with F star, but they are actually still not the same, actually far from the same. There are still some complicated indeterminacy locus on both sides. Okay. And then the question will be, how can we sort of resolve this map, or how can we see the difference between F star and the GIT moduli space? Okay, any questions?
So once you have you say that this is contraction, does it mean that it's a regular map or?
So it is contraction on an open set of HH and HU. So if you blow up, okay, so here's the thing. If you blow up these 2 points, then you get something model called M hat. So this is a blow up of M bar GIT at these 2 points. So 2Q and T.
Mm-hmm.
okay, which is in the
I
current.
see.
Then you have this rational map from F star to M hat, and this map here is isomorphism in codimension 1.
I see.
But you're still missing some locus. For instance, this M hat do not give you anything that is double cover of this quartic cone. You know, in the earlier classification, we see that the hyperelliptic one actually it has two locus. One is this covered by P1 cross P1, the other is P112, but we only blow up the point corresponding to P1 cross P1. So maybe I should say it over here that I'm blowing up Q. Here Q is a smooth quadratic surface. Yeah, so you don't see this 17-dimensional locus, which is double cover of quadratic cone in M hat, but it appears in F star. So you somehow need to flip them, and this is exactly what we want to do. I mean, one step of the whole program. Okay, does that make sense? Okay, so let me continue. Yeah, so then it comes to this prediction by Laza and O'Grady. So what they did is they try to understand how these two spaces, right, F star and MGIT are related. So they introduced this so-called Hasse-Kuo-Luyenda program. So it's kind of like a generalization of Hasse-Kuo program, which study birational models of MG bar. So the idea goes as follows. So we look at this type of variation of the Hodge line bundle. So we define lambda t to be lambda plus t over 2 times HH plus HU. So if you remember Hasse-Kuo program, you start from the Hodge line. It's not actually the Hodge line bond, but rather the log canonical divisor of MG bar, which is always ample, and then you kind of decrease the coefficient of the boundary divisor. And here we're doing similar thing, except we start from Hodge line bundle, which is ample on F or even F star, and then we sort of increase the coefficient of this, HH and HU, which are sometimes called Noether-Lefschetz divisors. And then what we do is so this is like their prediction. So first, you can sort of look at this, section ring of this lambda t. So here I always assume t is non-zero. Non-negative and rational number. And then they predict that this is actually finally generated. And moreover, if you take the approach of this R F lambda t, and they call it F, I think they call it Ft, then this is a birational to F. And moreover, there's a kind of an explanation of these spaces. So of course, first of all, you have F0 is F star. This is basically from the definition of Bailey-Burrell. And then if you go just a little bit to F epsilon here, my t is assumed to be, just a very small positive number. Then this means a morphism to F star. So this is a so-called Q categorization. of HH and HU. Maybe I should say, I'll put a star here. Yeah, because what happens in F star is at the boundary, it is very small. So you kind of don't have this nice Q factorial. It's very far from being Q factorial. So the divisors HH and HU at the boundary are very bad, but then you can sort of do a Q characterization. And then this is a small modification. And then 3 is if I go to 1, then I recover the GIT. So these 2 steps, they all verify it's okay. And then for 4, what we have is their prediction says there exists some explicit walls. And then there will be flips and divisorial contractions. And moreover, the exceptional loci will be some particular Shimura subvarieties coming from the self-intersection of HH union HU, but then you want to look at, so here I take a tilde, meaning that you want to look at the hyperplane arrangement in the period domain. So you have this quotient map from D to F. And then HH and HU lives inside F, and then you look at the pre-image. So it turns out HU is very simple. There's no self-intersection, but HH, there's like a very complicated self-intersection tower. And then you want to somehow flip every strata of this self-intersection. So it is pretty complicated in their prediction. All right, any questions?
Not yet.
All right, so now it's a good time to start with case stability. Yeah, so basically we want to study this question not directly from this Haskell Low-Angles program point of view, but rather from case stability point of view. So what we did is we look at K moduli of this pair, P cube P3, and then a constant times the quartic surface. So here, maybe I should give us some background. So case stability come from the study of Kähler-Einstein matrix. So this is algebraic criterion, or let's say algebraic condition for existence of Kähler-Einstein matrix. And then after many important works on this subject, especially from the algebraic point of view, we now have the so-called Fano K-moduli theorem. And this is due to many people, which I will list a few, and I'm sure I will forget some. So, sorry, again, from the very beginning, I forget some. Alper, Bloom. Maybe I should draw this. Yeah, this is by no means exhaustive, but I would just try to give my accounts. So Kodogny, and then Happen-Leisner. And then myself and Padafavi, and then Chen Yang and Zichuan. So if anyone wants to complain, I'm happy to add your name in or your friend's name in, but plus many others. Okay. Yeah. So what this theorem says is just a fix. If we fix some numerical invariant such that dimension, volume, and then maybe coefficients that. Oh, sorry, I forgot Chen Jiang. Yeah, my bad. Yeah. So then there exists a projective so-called good modular space. Parameterize K polystable log final pairs. So here K polystable is just the algebraic condition that is equivalent to the existence of Taylor isometrics by the so-called Yautian-Donaldson conjecture, which is now fully proved for log final pairs. And then this will be the main thing that we want to use to study this rational geometry of modular quartic K3 surface. So in the work with Kenny Asher and Christian De Fleming, we apply this whole machinery to this special case. So here, maybe I should explain our setup. So my S again is a quartic surface. So we always study this this K module as some kind of compactification. So perhaps you can start from general quartic surface, which is smooth, for instance. And then now my C is a constant between 0 and 1, which is a rational number. And then I just denote this modular space by M bar KC. So this is the K moduli compactification of P3 C times S. So so one thing I want to note here is that this modular space always contains the locus of ADE singularities, and actually it contains more. So this follows from interpolation of K stability. So pretty much for K stability, you know that it is defined using a so-called Futaki invariant, and the Futaki invariant is linear in the coefficient of the divisor. Suppose the divisor is like proportional to anti-canonical. Then you can show that if S inside P3 has so-called semi-log canonical singularities. So in other words, P3 S is log canonical by adjunction, inversion of adjunction. Then we know that P3 of S is a so-called K semi-stable log Calabi-Yau pair. So this is due to the work of Odaka. Of course, there's I think a new explanation due to the evaluative criteria of Peter and Lee. So pretty much the idea is in view of a evaluative criterion, K stability can be checked by this beta invariant, which is the difference between log discrepancy and this S invariant. So S invariant is some kind of volume function, and it becomes 0 if you're in the log Calabi-Yau setting. So then in this case, K stability just reduces to the non-negativity of log discrepancy, which is the same as being log canonical. And moreover, so by interpolation, we know that P3 of CS will always be is K semi-stable log final pair for every C between 0 and 1. And if, moreover, S has Duval singularities, so then in which you have P3S is PLT, then you have actually something even stronger. Then we know that P3CS is always K-stable. For every C between 0 and 1. So that tells us we actually have this containment. So M naught, remember, this is the moduli of quartic surface with Duval singularities. So that will admit open immersion into this SLC locus, which is again open, and then this admits an open immersion into this K moduli for every C between 0 and 1. And because here we care about compactification, you basically just take a Zariski closure of this locus, so you get a common like dense open set. Okay, any questions?
It's still fine.
All right, so now it's time to sort of study how to give these main theorems of our paper. So I call it theorem 1 due to Asher, De Fleming, and myself. So what we show is, okay, so let me start from this 0 part. So it says that there exists a finite sequence of walls. So 0 less than C1 less than something less than CK less than 1, such that you have the K moduli stay the same for C inside each open interval. And then if you change coefficient from one interval to the nearby one, so which we call wall crossing, then there are these directional morphisms. So Ci minus epsilon, it maps down to Ci, and then it maps from Ci plus epsilon. Yeah, so in some sense, this looks pretty much like a variation of GIT picture, although it is not globally variation of GIT, but only locally VGIT. Yeah, so this is proved in our earlier work for plane curves. And then now we go back to this quartic K3 case. So indeed, we figure out every wall, but this is the first wall. So if C is less than 1/3, then I actually have the moduli space to start with is just the GIT. And then actually, we also get, and C1 is 1/3. So, and then if you push through to almost reaching 1, because we want to study K-stability is log funnel, so C cannot be equal to 1, but it can be very close. So if we look at this coefficient 1 minus epsilon moduli space, then this is exactly the Q characterization of HH and HU in F star. So in some sense, we prove that this is isomorphic to the Luyenda in a modification as epsilon in terms of Lazaro-Gradis notation. All right, and then 3 is we can describe every wall crossing. So explicit wall crossing. So there are 2 divisorial contractions. Actually, it's a bit it's probably a reverse divisorial contraction, because as you see, we start from small coefficient, you actually get a smaller moduli space. And then if you grow the coefficient from 0 to 1, then it's kind of like an inverse process of MMP. So you will see blowups. So sometimes we also call it blowups. And then there are 2 blowups. So you have C1, which is 1/3, and then C5 is 9/13. So this is blow up center is exactly this 2Q, and then for C5 you're blowing up at, oops, sorry, there's something wrong with my pen. I'll try to fix this. One second. Okay. Let me try to share again. Okay, I apologize. All right, let's see if this works now. Okay, should work now. Okay, yeah. So let's continue. Yeah, so for C5 equals 9/13, you blow up this point T, where T is the tangent developed surface of this twisted cubic C0. And then there will be 7 flips, which is kind of complicated, but let's just put it this way. So the exceptional loci match Lazar-O'Grady's prediction.
So there are 9 walls, right?
Yes, there are 9 walls.
So K equals 9 in notation.
Exactly. So K equals 9. But actually, there are 10 walls. So if you think about M1 minus epsilon to F star, that's another wall, but it's like a small modification. So you can think about F star sitting at the end, which is on the last wall, which is the 1. Yeah. But the full wall.
So you don't cross it, you reach it.
Yes, you cannot cross it because from this setup, you reach the coefficient 1 case, and then if you increase the coefficient, in general, you will end in the KSBA region. But then here, because we have degree exactly 4, you cannot, there's nothing in the KSBA region because it's no longer a log canonical. Yeah, but if you work with quintic surface or even higher degree surface, then you do end up in the KSBA region. Yeah. But I guess in general, it's a conjecture. How are we going to construct this C equals 1 or C equals the log Calabi-Yau coefficient moduli space? So we have a big group working on it right now, and hopefully we can give some affirmative answer in some cases. Yeah.
Can you,
okay.
Can you explain once again part 2 in this theorem. So you have these two loci, divisorial loci, hyperelliptic and uni something.
Unigonal, yes.
Unigonal. So how do they fit into this blow-ups or blow-downs picture?
Yes. So I will give just a concrete description in a moment. Yeah. But let me first go to theorem 2. So theorem 2 is basically verifying Lazar-O'Grady's prediction. So from theorem 1, you almost see that this matches nicely with Lazar-O'Grady, except what we have here is these two divisors appear at different times. So in Lazar-O'Grady, perhaps I didn't say here. So what's going on if you look at f 1 minus epsilon, then this is exactly this m hat. So in some sense, in Lazar-O'Grady, at the end, if your t reaches 1, then these two divisors, they both sort of blow down to these 2 points at the same time. But for K-stability, we see them at different time. And the reason is, I think they have their singularity are not the same. So for instance, these two surfaces, they have different log canonical threshold, and turns out they have different so-called K-semi-stable threshold where you want to replace them at these walls. But nevertheless, we can sort of modify the K moduli, and then we can actually prove Lazar-O'Grady's prediction. So in fact, what we show is there are two things. So first, we show that M CK is actually the approach of the section ring of C lambda plus 1 minus C times this new divisor. So it's of different coefficient. And this sort of reflects in the K-stability wall crossing where you see these two divisors getting contracted at different time. So that's why this two coefficient, one for HH is 1/4, for HU is 9/8, they are different. But still modifying this this space, we can prove that that RF lambda plus, and actually we prove something even stronger. So we prove that you can have two different coefficients and they're still finally generated. Of every A and B positive. So therefore, this sort of recover Lazar-O'Grady's finite generation conjecture and the K-stability in the same picture where you have a two-dimensional. So this gives you like a two-dimensional wall crossing. Yeah, so pretty much what we work here applies to the cone generated by lambda, HH, and HU in the narrow severity group of your moduli space F, where inside this cone we show that finite generation holds, and there's a wall and chamber decomposition. Right, and then let me try to explain the replacement. So K stability replacements. So somehow you start from GIT, and then when you increase the wall, there will be certain GIT stable or semi-stable strata gets replaced. And then the corresponding replacing ones will be the following. So first of all, we have this space so-called XH, and that's nothing but the projective cone over P1 cross P1, and then with the polarization O1, O22. So this is anti-canonical cone over P1 cross P1. It's also toric funnel threefold. So your P3 certainly degenerates to this by deformation to normal cone. or degenerate, maybe I should say degeneration to normal. Yeah, so this cone looks like this, right? So this is your XH, and then the base will be P1 cross P1. But then the surface, the K3 surface, it will be a double cover of P1 cross P1. So somehow you can think about this as a kind of like a multi-section. So this will be my K3 surface. Yeah, so in some sense, we just enhance this this classical you know, type of this K3 surface. You have a sequence of generic ones degenerating to hyperelliptic ones, but this degeneration not only happens on the surface level, but also happens on the threefold level. So you have P3 and then some surface, and then you kind of degenerate to this. Okay, so this is the first, the threefold, and then there will be two more. So the second one is similar. Let me just write at the bottom. So the second one is this P1124. So this is again just the anti-canonical cone over P112. So this one will contain this 17-dimensional locus, codimension 2 locus, where your K3 surface. So here you see a hyperelliptic K3 surface that maps to P1 cross P1, and here you see all hyperelliptic K3 that maps to P112. So the degeneration is very similar. And then there's a third degeneration, which is we call it XU. So this is a very interesting one. So it's birational to a P123 bundle over C0. So remember, my C0 is just a twisted cubic curve inside P3. And then you imagine that your unigonal K3 surface gets contracted to this curve, right? And then if you want to recover the degeneration of the surface again into some threefold, then the natural thing to do is to take this P123 bundle associated to so-called Weierstrass model of unigonal K3. But this P123 bundle is not exactly the degeneration of P3. So what you need to do is you need to first blow up some curve, some section inside this bundle, and then you contract a divisor. So that's how you get this XU, and turns out this XU is a Gorenstein Fano threefold with canonical singularities, with just an isolated canonical singularity. And then theorem 3, which follows from this K moduli business, is that XH P1124 and XU are the only Gorenstein-Fano degeneration. Or maybe I should say Gorenstein canonical Fano degeneration of P3. Yeah, so somehow this theorem is proved using a kind of a different flavor as probably the classical study of Fano varieties.
But this theorem has nothing to do with modular spaces and, well, okay, except for the fact that XH and XU are constructed as modular spaces.
So the statement, of course, has nothing to do with modular space, but it turns out we give us a proof using modular space. So the idea of proof goes as follows. It's probably very easy, compared to what you guys usually do, right? Study like explicit geometry of linear series. But here we basically reduce this classification problem to moduli space. So the idea is if we have P3 degenerates to X, which is this Gorenstein canonical, then you can find one complement, or sometimes called elephant, I guess. There exists a divisor D inside X. Sorry, I should write it this way. So there exists a divisor D inside this linear series, such that the pair XD is PLT. Yeah. And then using K stability, you can show that X1 minus epsilon D is so-called K stable. So here you use Fujita-Lee criteria together with some kind of some other characterization using LC places plus my work with Bloom and Xu, whatever. So you can show that whenever you have a PLT pair, I guess starting from dimension 2, dimension 1 is perhaps false. Yeah, whenever you have a PLT log labial pair, and then you shrink a little bit the coefficient, then you get something K-stable. So therefore, this XD, they appear in the moduli space. And we know the moduli space for coefficient relatively small, and then you just follow the path of the wall crossing, you can describe everything. And then after you describe everything, you know these are the only threefold appear. So therefore follows from theorem 1. I guess I didn't state the corresponding threefold pair appear in the K module, but basically that's what we do. Does that make sense?
It does. But maybe, and can you, so this is very nice, the theorem looks very nice, and can you illustrate it, say how an analog of the theorem could look like in the two-dimensional case? How an analog of this argument could look like for P2 instead of P3?
Oh, okay. Yeah, that's a great question. So for P2, let me see. Okay, so here I think I use essentially Gorenstein, because otherwise you may have, for instance, all these magnetic surfaces that are degeneration P2. You can take a comb over it. These are not Gorenstein degeneration.
Yeah.
But in general, so for P2, if you want to find, say you want to look for this Q Gorenstein degenerations, then pretty much you have P2 degenerates to X, and then let's say I have minus M Kx is base point free. Okay, of course this M could be very large. Can be large. Perhaps depends on the index of your final surface X. So then you can choose some divisor D similarly inside minus MKX, such that this pair X, 1 over MD is KLT. Yeah, so over there we have PLT if M equals 1. But if M is larger than 1, you can of course usually have KLT section. And then you can show that X1 minus epsilon M D is K-stable. So therefore, this appears in the K-modular space of higher degree plane curves. And actually, we show that every magnetic surface appear in our plane curve modular space. Of course, your degree should be large enough.
Mhm. But
Yeah.
and do you have a similar? So okay, now this time you have like several modular spaces, right?
Yes, you have a sequence of modular space. Yeah.
Yeah. And
For each M, you have a modular space. Yeah.
and well, I would suspect that there doesn't exist. Am I right? There doesn't exist such a detailed description of all of them.
Ah, yes. So so far we only know something about a small degree. So for large degree, we can say, for instance, we know where is the first wall in this plane curve case, and perhaps in higher dimensions, there will be a similar flavor of where first wall appears. So first wall should always be conjecturally should always be replacing this 2Q here. So this guy, this 2Q, that should always be the first one. Even in higher degree. Well, I guess if you're in odd degree, then you don't have this guy. But then you add in like a transversal hyperplane. Yeah, but in general, in higher degree, it's very hard to describe all the walls. Although I think for the surface case, there might be a algorithm, a computer program that try to describe all this walls. So in dimension 2, because we know, so this is actually cheating. We are not really using case stability, but we have a classification of magnetic surfaces. So you kind of know the candidates that could appear in the modular space, and then you can write a computer program to sort of compute Futaki invariant. Yeah, so this way, for instance, I have done this program for degree 8 and perhaps degree 10. So you can sort of find all the pairs on sitting on the wall, because if you have a pair on the wall, then it carries a GM action. So it's not some arbitrary magnetic surface. It has to carry a GM action. So then in that case, your Futaki invariant becomes easier to compute. Yeah.
Okay.
But for P3, this is very difficult. So far, I don't know how to go beyond Gorenstein. So here we only know Gorenstein because then you're in this quartic case where we basically use K3 surface to figure out all the walls. But otherwise, we don't know how to proceed. Okay, perhaps I should stop here. Yeah, because I'm over time. Thank you very much.
Thank you very much, Yuchen, for an interesting talk with a very unexpected ending, I would say, because.
Oh, okay, thank you.
Are there any more questions? Well, maybe I have one more additional question, although I think you said something about this in the very, very beginning of the talk, but maybe I missed the message. So you started with K3 surfaces with polarization of degree 4, but this
Yes.
is not the smallest possible degree of polarization. There is also there could be a polarization of degree 2, right?
Yes.
And do you have a similarly nice modular space?
Yeah. So I meant to mention this, but somehow got dropped out. So for degree 2 case, what you have is a general one will be a double cover of P2 branch along a sectic curve. So C6, right? So this double cover. And then you can run the same argument. So so you just let M bar case C. I guess here I'm changing. Let me change my notation. Let me use P here. So this is the K moduli of P2 and then degree 6 curve, and then with the coefficient. So here my C is between 0 and 1/2 because I want the pair to be log funnel. So then it turns out this is again a joint work with Asher and Fleming in 19. So what we show is if C is less than 1/4, then you just get GIT. Or maybe I should use P. Always use P. P stands for the moduli space of, let's say, smooth or ADE cyclic curve. And then if C between 1/4 and 1/2, then this guy will be isomorphic to the sharp moduli space P hat, which is the blow up of the GIT at the triple conic. So 3Q. So triple conic, of course, log canonical threshold is 1/3, so you have to replace it. And then, therefore, this PK 1/2 minus epsilon is this blow up. On the other hand, it maps down to this F star of degree 2. So this is, I think, Q characterization of the divisor HU. Yeah. So you have a very similar picture, but it's just much simpler. You just do one blow up and then a small contraction that resolves the barrier.
Mhm.
Yeah.
Yeah.
So we expect this method to be can be run in like degree 6, and then maybe some other higher degree, degree 10, and then maybe possibly degree 22, although it seems very difficult. But then in the degree 22 case, maybe it can say something about case stability of V22, which still is conjecture. Yeah, but so far we're still in the very beginning of the stage. Yeah.
So the plan is to reach polarization of degree 22 and make conclusions and try to pull out of it an explicit discussion.
Yeah, so we want to describe a K moduli of V22, right? And for instance, now we have some cases of V22 we know is K stable or semi-stable, but we don't know. For instance, smooth ones are K semi-stable. That's still a conjecture. Yeah, but using K3 surface, maybe there's a way to sort of go around. Yeah.
Mm-hmm.
But I'm pretty confident on degree 6 case, which is a complete intersection of quadric and cubic threefold.
And can you just to feel the flavor of such an argument? So now you have the complete picture for degree 4.
Yes.
Could you use it to reprove the fact that all quartic threefolds, all smooth, say, quartic threefolds are K stable?
Oh, we only get we can only get some quartic threefold by taking cyclic covers. We cannot. This is quartic surface, right? If you take cyclic cover, you get some kind of special quartic threefold. Yeah.
But how then, in this case, but how do you intend to understand V22 in this case?
So V22 has the nice property that if you have a V22 and then you have a D, right? So this pair is if you map down to F22, then this is birational. At the same time, so this I'm talking moduli space. And then it maps down to V22 K moduli. And this is a certain, so I should say this is vibration of relative dimension 13. So this guy is a 6 dimension. Yeah, so if you can understand, again, you run this K stability argument, K moduli argument. But then if you can understand what happens for coefficient epsilon, then that admits, maybe I should put it this way. So this is only a kind of rational map. So if you put a 1 minus epsilon here, then you actually get a morphism. So this will be a morphism to star, F22 star. And then this will be birational. Let me try to rewrite it. So now you have a birational, most likely a birational contraction, although we don't know yet, to the K moduli of V22 epsilon D. And then this will be a morphism of fibration over the V22 K moduli. So therefore, if you can understand this part, which we do not know what this is. So if you can understand this part, then hopefully you can understand this. Does that make sense?
Yeah, so and the difference between, say, quartic threefolds and V22 comes in the very first line, right? Because if
Yes.
you take the pairs,
So for quartic threefold, if you take a Hartley section,
yeah, it's
don't-
a
you
high
do not-
dimensional vibration.
yeah, it's a vibration.
This.
So that's why we choose P3 rather than quartic threefold. Yeah. So, but one thing we can say is so-called quartic double solids. I guess I include this in my abstract. So quartic double solids, they are just V that branch along P3 along quartic surface. So therefore, their K moduli of these is actually isomorphic to the coefficient 1/2 K moduli of the pair case. And we have a description of this explicit. Yeah, so in this case, you have kind of like, again, a birational map from the K moduli of quartic double solids to F4 star, and you know the birational map explicitly. Yeah, so I guess this is a long shot, but we want to first understand the degree 6 from this point, and then see perhaps for higher degree it will be more complicated.
I see.
Yeah, we have the tools from K3 moduli theory, and hopefully it can help us to understand.
Okay, great. Are there any more questions to Yuchen? If no, let's thank our speaker and all other speakers once again.